Hi, welcome back to Book Club. Again, we're in Aircraft Engine Design, phenomenal book. And remember, as you're sort of reading it, it really starts at that sort of aircraft level handoff, sort of digging deeper and deeper and deeper down the systems engineering tree. And today in this video, we're actually now in the combustor. And when you think about combustion, really to help highlight this, if you look at a furnace, the number is somewhere around 10, all using English units here, but BTUs per second in a cubic foot. But then a gas turbine gets quite higher, and a rocket engine is even way more than this, right? A gas turbine is actually closer to like 40,000 BTU per second per cubic foot. And like I said, a rocket engine is way even more than that. And so these are pretty power dense systems. That's why they're great for aircraft. That's why even on power generation side, pretty useful. There's a whole line of power generation. GE has them, and others have them that are, they call them aeroderivatives. So they basically design the engine for an aircraft, and then with a few modifications, it makes a great power generation system. So that really, again, as I said before, aircraft jet engines in general are some of the most amazing technology that we of humanity has made. And so when you talk about the burner and the different things you want out of a combustion system, so the goals of combustion, let's sort of list them out. The first is you do want complete combustion. Not you don't want any hanging hydrocarbons or things like that. And we'll talk about emissions here in a second, but just from a pure, like, I mixed the fuel with air, our oxidizer, and had combustion. You really want the full complete process in that combustion. So that'll drive a lot of design. Okay. Secondly, you want very moderate, is what they use in the book, moderate pressure loss. And so there are combustors you can design that really have great completeness, or all these other things we'll talk about here in a second, but they'll have a pressure drop. No, the full system is sort of that thermodynamic balance of suck, squeeze, bang, blow. If you lose too much pressure to do that, it doesn't work out. In fact, a lot of things as we talked last time, the sort of heat transfer side of things, where you might be able to cool a blade better if you used up more air, but then that's air that's not being mixed in. It's also pressure drop and things like that. So a very important trade. Third one is stability, and this means no flame out. Stuff stable. We'll just write it like that. I heard a story of an engine design that was like all the way to the point where either this was sort of initial trials with the aircraft, or maybe they had already delivered them to the fleet. But the story was an aircraft that is sort of turned to get ready to take off, and there was a gust of wind from behind. Normally an aircraft is turned facing the wind, and so either during taxi or something like this, the wind blowing backwards went up the engine and flamed out the combustor, so they had to restart the engine. And so things like that, handling a gust from behind, kind of going back up in the engine, they had to do a bunch of changes, and I forget what engine company that was. So that's important, and along with that, like I just mentioned, is the ability to relight. So it can be as simple as that scenario I just described, where it flamed out on the taxiway, but certainly relight in air is very key. And it can be complicated. Now, there are some conditions to relight. You have to be under this altitude. In fact, I was talking to a pilot who had an engine out. It was a twin engine. They had an engine out at 37,000 feet. So their first step was a slow descent, but they slowly descended down to 25,000 feet to relight, and they couldn't get it to relight. There's a longer story there, but not mine to tell. So that's key and important. And then really you want at the combustor exit, and this is where I'll now kind of pause and draw my combustor below. You want a smooth temperature profile. Okay, so all right, so here comes the Andrew design of a combustor, and so you're getting your velocity in the air from the last compression stage. I'm going to draw it here, and there is a diffuser. So normally what you're doing is sort of opening this up. It is subsonic, so you're opening up to slow it down, because you're going to bring your fuel in like this, and then ultimately, here is sort of your combustor can. And then I'm going to change colors here to orange to sort of highlight a few things. And so some gaps like this. Okay. And then what I'll then highlight in blue, which should turn out okay. This is sort of the primary, so I'll say that's number one. And is that coming out well? Yeah, it's coming out okay. And this is sort of your secondary combustion zone. And then this is also then called the diffuser. And then you're going to bring this back out and then mix it. And then this is going to go into the turbine. Okay, so that's from the turbine. This is from the compressor. And so a couple of things. Combustor exit temperature. That's after you've done all of this stuff. You really want this to be pretty smooth. No hot streaks. Because again, the temperature here is going to be above the melting temperature of this turbine. That's why the sort of intercooling of that sort of first stage turbine was a really exciting sort of research project. A lot of things to do here to improve the performance, both from a pressure drop, but also heat transfer side of things. Okay, you do actually want a short length. This is just related to the weight of the system. If it takes forever, that's again all of this, whether it's the axle of the turbine or the shell casing, all of this, if it grows in length, it grows in weight. So you do want this all to be pretty short. And then just like all of these other systems, remember our off design video? So you want this to be able to handle all of those off design scenarios. So that's in terms of flow rates, pressures, temperatures, you name it, rain, right? All of these things that we would consider off design, but it's really, again, that's kind of the wrong word. It's sort of, it's very operational. In order for this thing to work, it has to handle all of these conditions that it's going to see, especially for aircraft engines, it's going to see on every flight. It's very different if this is like power generation, it's at sea level, or even if it's at 3,000 feet, whatever it is, like the very fixed condition, even if the sort of Earth temperature is changing. What you see in flight with all these altitude changes and humidity changes and rain and all those things is actually quite different. And then, yes, of course, pollutants. Now, I know recently there's been quite the interest in CO2, but just to remind everybody, our interest about 30 years ago was all about NOx. And so that is still a requirement. We are still interested in NOx reduction because of our ozone layer and things like that. And so it's really this combination of, say, generic pollutants. It's NOx, it's CO2, but it's also these unburned hydrocarbons. All of these things you have to go do and take care of, and different regulations that'll sort of drive that. Okay, so that's the main kind of the main challenge with combustors. Now, a lot of times what they do here, this is where the fuel is kind of coming in, and they'll put a lot of swirl here. And so really what you're creating is sort of this recirculation bubble. And the book does a good sort of diagram of all this. You're creating a recirculation bubble for the flame to hold. Now, also through here is where the spark is going to be. They'll draw a little lightning bolt. Okay, there's my lightning bolt. So spark is going to come in there and light this. And really, you're looking for, usually it's a laminar flame, which means a very smooth flame. Very different than sort of a turbulent flame that's got all these fluctuations. So laminar flame, you need to usually you do this fuel rich, okay? And so you're going to do fuel rich to sort of have good stability, all these different things, but then the air that's coming around it, you're going to quench it lean ultimately over here for emission control. But throughout this, air is going to kind of come in through these slots. So it's going to come in to these dilution holes and come in, but it's also helping keep this this kind of combustor liner from melting again. So you have coolant of the air going across, but also these kind of coming through the holes, kind of starting to dilute that flame a little bit, and then ultimately quenching lean here for emissions. So fuel for stability, quench lean for emissions. Yeah. We talked about these. Where did it go? Complete combustion. So I'll actually sort of draw it up here. So again, you have your stoichiometric ratio, and so you've got some sort of hydrocarbon. So CXHY, if you were going to do the full version, it depends on what X and Y is. And of course, we're adding air. And so yes, this is O2, but it's also that fraction of nitrogen, okay? And then that's going to turn into, yes, you have all the standard things, CO2, but also CO and water. You have extra oxygen that didn't get burnt. You have sometimes, you can have oxygen radicals. And then you have all of your sort of your NOx chain, okay, plus all the stuff. So this is sort of the full complete set. And so it really depends on what the propellant is, the different combinations, and your full emissions. So complete would mean you don't have any of these unburnt hydrocarbons, Of course, there's all your pollutants coming in. And then off design would also need to include this one here, right? So that's actually your throttle. That's how much fuel you're putting in. So if you go leaner, how does it change? So those are the big ones. Now, if I draw an afterburner, right? So the end of sort of your jet engine. So here's your jet exhaust. You then can have an afterburner channel. We've drawn this before, and likely you usually have these kind of flame buckets. And the same sort of thing is going to happen. This air is now still hot, and so by adding fuel, and you can get it to light, effectively you're adding fuel, it auto ignites. Now, usually what happens here, let's say you might 2x your mass flow rate. You probably can't see that. Try it again. So you might 2x your mass flow rate, but you may also, and maybe even more, but you're going to likely sort of double your thrust as well. And so usually it's a combination that works well in terms of the from those military missions, again, kind of driving down from the vehicle level, especially for aircraft that need to get past the sound barrier. So getting past the sound barrier without an afterburner, doing it fully dry, it's challenging. It's possible. It's challenging. Really, they've got to be pretty powerful engines. Okay, and then really from we want to kind of talk through also all the different fuels. Now, here's all the list of sort of the Jet A, JP5, JP6. I usually am pretty agnostic to a lot of this, but it's because I'm not a pilot and operator. A lot of these will the big differences. Yes, there's differences in the chemistry and things like that, and the additives. A lot of it is actually sort of this flash point and then the freezing point, and controlling both. Okay, and you can kind of see all the special blends. So the JP7 in particular was the one for the SR-71, and right, it was designed because it went to higher altitude, so it needed a little bit more stability. This table, I believe, is flash point at sea level, which is different than flash point at altitude. So the military normally is JP5, but then they also carry some JP8. And then here at the airport, like here at Ellington, it's just Jet A, just sort of generic. Again, most of this is all kerosene for the most part. It's just all the extra little bits and bobs in that kerosene. A rocket, in the rocket world, that's what RP1 is. It's basically, Jet A, where they filter out all of the junk, and you're really just left with almost pure kerosene. You're still allowed to have a little bit of junk. Some of it's hard to get rid of. Okay, and then this diagram is a good diagram talking about sort of the challenges of that operation and then combustion temperature. I was talking about sort of burning fuel rich for stability and combustion, then quenching lean. And you can see here that the combustion temperature in terms of where are you sort of minimizing your NOx and your CO2. That kind of gives you an idea here of where you might want to operate. But then based on your throttle and things like that, you have all these conditions. So this lean blowout would be where you're throttled down too much, or the right kind of conditions. You could have issues. So that this all gets pulled in. There's really this level here where it's starting to get pretty designed, because now we're talking about the combustor. But this is really just the start of if you're a combustion scientist, this is just the start. But there are entire textbooks and entire fields of studies on combustion and the combustion kinetics. Like this is not even complete. And you may have heard me talk about this before, where I think the full combustion kinetics is probably like a 3,000 set of differential equations to account for all of the possible bits and bops, and its full balance. So you can get quite detailed, and again, there's still I still feel like there's a lot to be learned in combustion science, a lot of room left. Anytime you have something that's sort of that black of a box, it means there's usually room left to go improve. And then I'll sort of finish with SAF as a sustainable aviation fuel. And really what this is doing is taking multiple feedstocks. And so that's corn or trees or whatever the feedstock is, but also you see here this diagram of hydrogen and then syngas, CO2. So taking this stuff and converting it into jet fuel. Now, one of the open questions is like, well, if you're starting with hydrogen, where did you get your hydrogen? That's why hydrogen production has all of these colors. There's sort of shows you that. I don't even remember off the top of my head, but some of them refer to like you got it through a very green process. Like I had a hydroelectric dam generate power, and I used that power to split the hydrogen. Things like that. That would be one color of hydrogen versus I got my hydrogen from, the fuels coming out of the ground from dinosaur juice, if you will. Okay, but really, synthetic aviation fuel is using they sort of, taking the CO2 from the atmosphere, using these sort of natural things and creating the fuel through these waste products, converting it to SAF. And the start here, this part where it says blending it with jet fuel, that actually comes back to really it's the combustors. So in the end, SAF is a different blend of all the little bits and things. Like it's kerosene with a slightly different blend. And a lot of the combustion stability is actually due to those very particular blends. So that's a lot of what they're doing right now, is just trying to blend the SAF where the existing engines don't need any modifications. It's a very different story to then go develop an engine, which is really developing the combustor to take pure SAF, and where it can do all this stuff. All of these things above, we're running just a pure SAF engine is slightly different. And then they talk about transport and the fueling of the aircraft. And there's a whole economy behind this, right? People are making SAF. Like we got a bucket of SAF here. We're going to fire through our detonation engine. So people are making SAF. The challenge is actually the cost of it. And some of the cost is supply and demand. So there's a broader story that I'm going to get into, but this is certainly one of the ways of we're going to be able to get carbon reduction. People will talk about hydrogen aircraft. The challenge with hydrogen aircraft is just hydrogen is not very dense. I talked through this during the Kuchumon lecture series, and it's just your vehicle designs are not going to go far. It's just the size of look at the space shuttle, the size of the big orange tank. Any of these hydrogen aircraft, if they're fielded, they're going to be regional. They're not going to have enough range to say cross an ocean, and so. Hydrogen aircraft may be part of how we reduce our carbon footprint, but SAF is certainly a way, for those long range flights. It's certainly going to be SAF or nothing. So it's an important technology, and we'll see where the cost of it goes. We'll see what people, what the market is willing to support in terms of extra costs. But it's a big challenge. Lots of work going on, and this is just a touch. So go read through again. It's a good chapter on kind of getting you into the basics. And I just kind of hit the wave tops here. So go dig in. And we'll see you next time. We've got one more lecture series on this book. See you next time.